Good day, everyone. This is again Roger. In our fluid mechanics today, we'll discuss about ideal gas law. In our chemistry, we'll learn about the ideal gas equation. We have this Boyle's law, that is, the pressure is inversely proportional with the volume at constant moles and temperature. Charles' law states that the volume is directly proportional with temperature at constant mole and pressure. And the Avogadro's law states that the volume is directly proportional with our moles at constant pressure and temperature. So we can combine these laws into this relationship that volume is directly proportional with moles and temperature, but inversely proportional with pressure. Given the relationship, we can derive an equation by adding a constant. So now the volume becomes some constant times the number of moles times the temperature over pressure, where our constant is given by this R, which we call the gas constant. Now, the ideal gas law equation states that the pressure times volume is equal to moles times the gas constant R times the temperature. So pressure is in kilopascal and volume is in liters, and N is moles and T is the temperature in Kelvin, and R is our gas constant, which is equal to liters atmosphere over mole Kelvin. Since gas law equation is equal to pressure times volume equals nRT, let's discuss first absolute pressure, because every time we'll use pressure, we should have an absolute pressure. So what is absolute pressure? Absolute pressure is zero reference against a perfect vacuum using an absolute scale. So it is equal to gauge pressure plus atmospheric pressure. So your zero reference is the perfect vacuum. So it's gauge pressure. The gauge pressure is zero reference against ambient air pressure. And the standard sea level atmospheric pressure is equal to 101.33 kilopascal. For example, if you are in an airplane, inside the airplane there's a gauge pressure. And outside of the airplane, there is an atmospheric pressure. So the absolute pressure of the airplane is different from when it is in the ground and when it's in the air. Standard temperature and pressure. So the condition where at 0 degrees Celsius and 1 atmosphere are called standard temperature and pressure, or STP. Experiments show that at STP, 1 mole of an ideal gas occupies 22.414 liters. Since we knew that at STP, the volume is 22.4 liters. So now we can derive the value of our gas constant. Rearranging our equation, so R is equal to pressure times volume over mole times the temperature. So at STP, we have 1 atmosphere times 22.4 liters over 1 mole times 273.15 Kelvin. So therefore, our gas constant is 0.0821 liters atmosphere mole Kelvin. Now, in molar form, we have pressure times volume is equal to the mass over the molecular weight times our gas constant times temperature. So rearranging our equation, we have pressure is equal to m over v times RT over m. So our m over v is equal to our density. Okay, so we have now left with pressure is equal to density times RT over m, where R, our specific gas constant, is equal to R over m. Okay, so this is R over m. So now our P, our pressure, is equal to the density times our specific gas constant times the temperature. So sometimes it's not specified that it is a specific gas constant. So all you have to do is look if there's no volume, then we must use this specific gas constant. So now this is our table for our gas constant. For example, we have here the air, which has a value of 286.9 joules per kilogram Kelvin of specific gas constant. So these are the common gas. So we have here a problem. We have the compressed air tank shown in the figure has a volume of 22.65 liters. The temperature is 21.1 degrees Celsius and the atmospheric pressure is 101.35 kilopascal. So when the tank is filled with air, the gauge pressure of 344.74 kilopascal. So determine the density of the air and the weight of the air in the tank. So our unknown is our density and weight. So here's the solution of our problem. So from pressure is equal to density times the specific gas constant times temperature, we can rearrange this one to have density is equal to pressure over RT. So we just substitute our given. So our pressure should be absolute pressure. So we'll need to add our gauge pressure plus our atmospheric pressure. So our gauge pressure is equal to 344.74 kilopascal and our atmospheric pressure is 101.35 kilopascal. And our specific gas constant is 286.9 joules per kilogram Kelvin. This is for air times our temperature, which is 21.1 degrees Celsius plus 273 so that we can have a Kelvin. And then our final answer is 5.29 kilogram per cubic meter. This, our weight is just density times gravity times volume. So we solve that our density is 5.29 kilogram per cubic meter multiplied by the acceleration due to gravity, which is equal to 9.8 meter per second squared, times our volume. We are given with the volume 22.65 times 10 to the minus 3 cubic meter of volume. So our weight is equal to 1.17 Newton. Right? Thank you for listening and stay tuned for more updates in this topic.